Hi everyone, I'm Niels Bantilan, and I'm excited to present to you at PyCon this year. Just to give you a little background about myself, I'm one of the core maintainers of Flight, which is an open source machine learning orchestration tool, and I'm also the author of a data frame validation tool called Pandara, which is something I'll return to a little later. I want to start my presentation by making the claim that type systems help programmers reason about and write more robust code. Since Python takes a gradual typing approach, you can opt in to using type hints, and I found that they improve readability and help me build a better mental model of what my code is doing. To see the benefits of type hints, if you take a look at this code snippet, you can see that we're defining a function called add and double, which takes two numbers, either an int or a float, and then outputs another number, which is presumably the sum of the two numbers multiplied by 2. Now, I want you to take a few seconds to ask yourself, just with type hints and no actual implementation in the function body, can you predict the outcome of these function calls? We'll review this again later, but now I think we have enough context to get to the central question of my presentation, which is, what would a type system geared toward data science and machine learning look like? To address this question, I'm going to introduce you to some of my problems, define a specification for data types in the statistical domain, demonstrate one way it might be put into practice using Pandara, and discuss where this idea can go next. So first, let me introduce you to some of my problems. There are three. The first one is that the worst bugs are the silent ones, especially if they're in machine learning models that took a long time to train. To see why, consider the notion that statistical models are some kind of compression, representation, or approximation of the data. This implies that if the data changes, the model changes as well. So really, when I'm using a model for explanatory or predictive purposes, at a high level, we're really using the model as a function that takes some input x and produces a result y. Now the question is, how do I know if f is working as intended? There are many answers to this question, but here I'd like to highlight two approaches which are well established in the software development world. The first approach is to catch certain type errors statically, even before running any code. So let's return to this example I showed you in the beginning. Since Python 3.6, we've had type hints and tools like MyPy, which can identify errors like the middle example here, which invokes add and double with an invalid type, namely a string hello. But what if the underlying implementation is wrong? Type hints can only get us so far because the first and third call to add and double are valid invocations, but the actual output is incorrect because the function body implements the wrong logic. This is where unit tests come in. Unit tests verify the behavior of isolated pieces of functionality and let you know when changes cause breakages or regressions. As you can see, I've divided up my tests in terms of happy and sad path tests. In the happy path tests, I've manually written examples of valid inputs and then test whether the output is correct. And then in the sad path tests, I've defined cases that should raise some sort of exception. Note that actually these sad path tests right here are actually redundant, since the type limiter should be able to catch type errors. You might have noticed that it's actually quite burdensome to write test cases explicitly. So another thing we can do to be confident that my function works is to define property-based tests. Here, I'm using hypothesis to define the interface of my function as type strategies. There's actually a tutorial here at PyCon this year that focuses exclusively on the hypothesis library and property-based testing. so I'd recommend checking that out. But here I'll just give you a gist. When I run my test suite, under the hood, Hypothesis generates a bunch of data according to those types, and then attempts to falsify the assumptions made in the test function body. And if it does so, it then tries to find the smallest human readable example that falsifies the test case. All this talk of testing brings me to my next problem, which is that testing code is hard, but testing statistical code is harder. To see why, let's look at a toy example where we have a system that ingests survey data, stores responses in a database, then creates a dataset and trains a model to predict a target of interest. Now here's what your pipeline might look like. And to help with readability, I've defined two types. One that represents the process response, and another that represents a training example, which consists of a list of floats for the features and a Boolean value for the target. If we just focus on the store data and create dataset functions, you may notice that store data's scope of concern is atomic, in that it only operates on a single data point. On the other hand, create dataset needs to worry about the overall statistical distribution of a data sample when it creates a dataset for modeling. Now, going back to the idea of unit testing to be confident that our model works as intended, I'd ideally want to test with some data that looks reasonably close to what I'd see in the real world. So what if I want to test create dataset on a plausible example dataset? Unfortunately, the main answer here is you need to handcraft example data, which often takes the form of pandas data frames. And the most I'll say on this topic is it's not fun. Ideally, what I'd like to be able to do is specify the data types of my variables as a schema along with additional constraints. Here you can see that I'm importing Pandera, and I'm using it to define a schema for the survey data in our toy example. I'm making sure that questions 1 and 2 have values of 1 through 5, and I'm making sure that question 3 matches some regular expression. I can then use a schema to both validate the properties of some data at runtime and also sample data under the schema's constraints for testing purposes. Now, the code you saw in the previous slide is all valid Pandera syntax, but actually, before diving further into Pandera as a specific implementation, I want to first define statistical typing more generally, with a few examples to illustrate what I mean. I define statistical typing as a type system that extends primitive data types like booleans, strings, and floats with additional semantics about the properties held by a collection of data points. So for instance, the Boolean data type consists of two possible values, true and false. In statistics speak, we would call this the support of a particular data distribution. Now, we can extend Booleans to Bernoulli types. And to do that, we'd need to supply just one more piece of metadata, which is a probability mass function that maps values to probabilities, all of which must sum to 1. This is sufficient to specify a Bernoulli distribution that we can name, for example, a fair coin type. And you can imagine assigning a variable of this type to some data, and then performing statistical operations on it, for example, getting the mean or mode of the data. We can generalize Booleans to enumerations, which gives us a way of expressing a type with a finite set of values. For example, we can define a set of animals consisting of cats, dogs, and cows. Enums can be extended to categorical types by again providing a probability mass function, as you saw in the previous slide, in addition to a flag that indicates whether the values are ordered or not. Here you can see we're defining a farm animals type with a particular distribution of animals that you might find at a farm. you can imagine doing runtime type checks on data associated with the animal farms type to make sure it follows the specified distribution. The last example I wanted to show you is extending floats into Gaussian types. This is conceptually simple because all you need to specify a normal distribution or a Gaussian distribution is the mean and standard deviation. And here we've defined a tree height type with a mean of 10 and a standard deviation of 1. The cool thing about these types is, just like the property-based testing example that I showed you earlier, I could potentially use them to sample data for the purpose of unit testing. So if I have a function that processes data drawn from the tree height distribution, I should be able to draw samples from this type, pass it into processed data, and then make assertions about the result. Now, I'd like to make the point that statistical typing isn't really new. When I first thought of the term, I Googled around for a bit, and to my surprise, I could only find 1 or 2 blog posts that specifically used the term in the same way that I was thinking about it. To prove this point, I want you to consider the following code snippet. And don't worry too much about what the function actually does, just look toward the end. If you've ever written assert statements that do runtime validations to check whether the output fulfills certain assumptions like value ranges or other such properties, then congratulations, you've been doing statistical typing all along. So we can try and codify a few of these ideas, and we can think of statistical types as potentially multivariate schemas, where for each variable, I can define a few things. The primitive data type, a set of deterministic properties that the type must adhere to, and a set of probabilistic properties, such as the distributions that apply to the variable along with their sufficient statistics. The implications of a fully implemented statistical type system are that some statistical properties can be checked statically. For example, you can't really apply the mean operation to categorical data. And yet other properties can only be checked at runtime. For example, whether a specific sample of data was drawn from a Gaussian distribution. And finally, the schemas can actually be implemented as generative data contracts that can be used for both type checking and data validation, and also sampling. To illustrate this last implication, it's time to look at a concrete example using Pandera, which I'd say is a rough and somewhat incomplete implementation of statistical typing, but many of the ideas are there. So suppose we're building a predictive model of house prices given features about different houses. You can see from the raw data that we're working with 4 variables: square footage, number of bedrooms, property type, and price, which is our target variable. We can think of our pipeline in 2 steps, the first one being to process the raw data, and the second one being to train a model on the processed data. And now we can define schemas in Pandera, which in practice actually requires a little bit of data exploration to get a sense of what the data look like. But here we are defining a base schema, which we'll use as the foundational type. And we'll have our raw and processed data schemas inherit from it. From these schema definitions, you can immediately see which variables the raw and processed data have in common, which is these 3. But you can also see what the differences are, namely that the raw data schema has a property type variable containing strings that need to be converted into a set of binary indicator variables. We can then add type annotations to our process data and train model functions to make sure that the inputs and outputs conform with the schema definitions. And we can fill our functions in with actual implementations. And here I'm using pandas and sklearn to process and train a model. Now the cool thing about this is that our processing and training functions now inherently validate our raw and processed data every time we invoke those functions, for example, when we run it in our pipeline. And if we happen to ingest invalid data, the pipeline fails early and we're provided useful information about what exactly went wrong, in this case, an unknown value in the property type column. And to circle back to property-based testing, Pandera exposes a strategy method that compiles the schema metadata into a hypothesis strategy that you can use in your unit tests. This becomes useful because in the case that we've implemented something wrong, we'll get a useful error message too. Here, Pandera is complaining that the output of processed data doesn't contain the property type condo variable, which is the case because we've wrongly implemented our function to just return the raw data instead of actually processing the data. And finally, you can even bootstrap a schema from a sample of data because it can be tedious to write a schema from scratch. All you have to do is call the infer schema function, which you can then write out to a YAML file or a Python script to further edit and refine. To sum up the practical use cases of statistical typing, and Pandera in particular, you can use it in the context of continuous integration tests for your ETL or modeling pipelines, but you can also use it for alerting when detecting dataset shift, or monitoring the quality of your model's predictions in production. But to go from practical use cases into theoretical applications, I want to end with a few ideas that might be interesting to consider when thinking about the question of type systems for data science and machine learning. The first idea is that it would be really nice to be able to statically analyze code in order to call out cases where statistical operations don't make sense given some type. So returning to the farm animal example from earlier, this would mean that even before running code, we could tell that computing the mean of a categorical distribution doesn't make sense, and our type linter should be able to tell us that. The second idea is that it would be possible to infer the model architecture space based on function signatures with statistical types. So in theory, if I have a function that takes a Gaussian distribution as input, and then outputs a Bernoulli distribution, we should be able to infer the space of valid model architectures that could approximate this function. And finally, maybe the wackiest idea is to infer statistical types from data. And the rationale behind this is that it's not always the case that my data can be neatly categorized by the theoretical statistical distributions we know about today. For example, image data or natural language data might be drawn from a very complex manifold that would be impossible to write down manually. In this case, we would want a schema inference routine that can be arbitrarily complex to describe statistical types that can also be arbitrarily complex, using data that can be encoded as a statistical model where the artifacts can lend themselves as components in a schema. So to illustrate this final point, let's consider generative adversarial networks, or GANs for short. In theory, a GAN can be used as a schema to validate real-world data, but also generate synthetic data. The way it works is during training, you draw real samples from the real world, and then fake samples from a generator, whose objective is to fool the discriminator into thinking that its synthetic data is real. Conversely, you have the discriminator whose objective is to accurately tell when a data point is real or fake. Typically, after training a GAN, people only care about the generator and discard the discriminator. However, in our case, we can actually use the discriminator to validate data by telling us whether a particular data point is real or fake. We can also use the generator for its primary purpose of synthesizing data for testing our model training functions. In effect, this would imply that we can implement validation in data synthesis modules for complex statistical types. For example, an image dataset with a particular set of categories describing those images. In theory, it would be possible to define a schema like this, where we have an image type that points to a JPEG file. And at validation time, that file is read into memory and passed into a GAN to verify that the image is drawn from a similar distribution as what we saw during training time. This might be useful in production to at least warn us when an image is out of distribution. So I'm hoping that in this last section, I've given you some food for thought. And really the main takeaway I want to leave you with is that statistical typing extends primitive data types by enforcing a set of deterministic and probabilistic properties that must be held by a collection of data points. This opens up a bunch of testing capabilities that make the code that we write as data scientists and machine learning practitioners more robust and easier to reason about. And with that, I'd like to thank you for your time and attention. Please feel free to reach out to me via email, Twitter, or GitHub. And I hope you got something out of this talk. Enjoy the rest of your conference.